Okay, so now I'm going to start by teaching how to find the domain of arcsine of the quantity of x minus 2 divided by 3. So generally when someone teaches how to do this kind of question, they teach a pretty simple approach, assuming that you already understand arcsine. But I'm pretty confident that almost 90 to 95% of people who ever encounter these kind of questions, they don't understand inverse trig because it's taught in such a weird way, and very few people are able to completely understand or retain the principle behind it. So to answer this question, I'm going to actually teach you how to understand inverse trigonometry using arcsine as my example. So first, I'll start with the graph of y equals sine of x. So y equals sine of x is a sinusoidal function, obviously, and the fact it is a function is proven by the vertical line test, where if you draw the vertical line at any single point, or any single point along the domain, you will have a pass, because there's only one corresponding y value. When you take the inverse of a function, that means you're pretty much going to be rotating in 90 degrees, and then flipping it about the universal y-axis. So you can see here I call this hypothetical y equals inverse sine of x. And if I was to do the vertical line test, it will fail without a doubt because there are an infinite amount of values that could be for the same x value, which means that the range is pretty much infinite and the domain is limited. So there's a problem here. This is not a function. So to get around this, what mathematicians have done is that they take only a portion of y equals sine of x, which is between negative pi halves and pi halves. And they actually take this as the bounded values for y equals sine of x. So what actually makes this unique is that this gets only part of a sinusoidal cycle, which means that all the y values in the situation will be unique because there's no dip. So to illustrate this, here is a hypothetical sinusoidal function. Obviously this is not exactly y equals sine of x. But if you're to take the inverse of this, which would be turning this over and flipping it relative to this axis, we'll pretend that it's flipped over. It doesn't really matter in the situation. You can see that you have two y values existing for the same x value. Whereas if you looked at it in the original function, this is not the case. It's still a function because the vertical line test would pass every single point. So with this representation of y equals sine of x bounded by these intervals in the domain, you can see that if you were to do the vertical line test, when you flip this over, you'll still have unique values, which means that it maintains its status as a function, which means it's an inverse function. So this is actually very special because you're actually finding out how the concept of arcsine comes to be. So y equals arcsine of x looks like this, where you have the domain flipped with the range. So it starts from -1 and goes on to 1. And the range values start from negative pi halves and go to pi halves. So one of the rules of thumb with all forms of inverse functions is that all the x values and y values switch places when they're inversed. So for example, with y equals sine of x, if you have x is equal to negative pi halves, the y value is equal to -1. But with arcsine of x, when x equals -1, y equals negative pi halves. With 0 at the origin, there's no real, you can't really notice the difference. And when you go to pi halves, well, when y equals sine of x, when x equals pi halves, y equals 1. And with arcsine of x, it's the reverse of that. So this actually affects the domain as well. So with limited domain, I call this limited domain because we only took an interval of y equals sine of x. We took it over negative pi halves to pi halves, which also had a corresponding range, which is the range of all sine functions, assuming they're not transformed, is going to be -1 to 1. So the thing is, arcsine swaps these positions. So the domain actually becomes the range, and the range becomes the domain. So then you can see that the domain is actually -1 to 1, and the range is negative pi halves to pi halves. So then we should understand the rest of the function. So the original question was actually asking about arcsine of the quantity of x minus 2 divided by 3. So we already understand that the domain and range are going to be limited by these values. But the thing is, because this is not arcsine of x, this is arcsine of a different transformation of x, the domain will change while the range may stay the same. So the domain is actually related to the domain of y equals arcsine of x. So by dividing this x term by 3, the range multiplies by 3. So it changes from -1 to 1, and that transforms into -3 to +3. So by dividing the x, it stretches the function, while multiplying the x, it shrinks the function. And by subtracting the 2, when you have x minus 2, the domain shifts by 2 units to the right-hand side. So the domain goes from -3 to 3, to negative 1 to 5. And this seems like a lot of words and probably very difficult to understand. So what I did is I'll actually show you these transformations step by step. So this is I'll call it vanilla, y equals arcsine of x, with a domain being from negative 1 to 1. The moment you divide this by 3, the domain stretches, so that negative 1 to 1 turns into negative 3 to 3, whereas the range stays the same. Now, if you're to look at arcsine of x and then just subtracting 2 from it, this actually shifts the domain. So originally the domain started at negative 1, and then right, negative 1, and ended at positive 1. So that shifts 2 units to the right. So this would be the origin that's located here. So you move a 1, 2 units to the right. And you have this same exact function, same exact intervals for the domain, but it's just transformed to the side. So we have this shift to the right, and also a stretching occurring in this function. So arcsine of x minus 2 divided by 3 is going to start at negative 1 and end at positive 5. It's the combination of both these guys. So how can we mathematically represent this? Because we found the domain pretty much. The domain is going to be negative 1 to positive 5. So there are 2 ways that we can solve this. One is the kind of idiot way to do it, and one is the more intuitive way to think about it. I'll show you the idiot way first, because the idiot way makes lots of sense just to get an answer. And the intuitive way gives you a universal method to solving this question. So you could do that x minus 2 divided by 3 is equal to positive or negative 1. Because the original range for arcsine of x is going to be negative 1 to positive 1. So we can find the extremities based off of this. So when you have x minus 2 divided by 3 is equal to 1, and x minus 2 divided by 3 is equal to negative 1, you get the values of x equals 5 and x equals negative 1. So the domain has to exist between both of these 2 values, and the domain then turns into negative 1 to 5. Now the more intuitive way to think about this is, with x minus 2 divided by 3, you know that the values will exist between these 2 values. So why not just do this one giant inequality? So you first multiply both sides by just positive 3. So you have negative 3 is less than or equal to x minus 2, which is less than or equal to 3. And then you can just add 2 to both sides. So negative 3 plus 2 is going to be negative 1, and 3 plus 2 is equal to 5. So these are all the real values of the domain. Hence, the domain is equal to negative 1 to 5. So by understanding the basics of inverse trigonometry, you can actually figure out the domain just by understanding what this function is relative to what this new function is relative to the normal x value functions.